Good day to doctor. We are from group 1. So today we are going to present our numerical methods project. So before I continue my presentation, let me introduce first the group member for group 2. Wen Jiakwan, which is our leader, and Qin Jingsun, Ethan Zhong Zhenyu, and me, Sun Wei Shuang. Okay, so let's take a look for the overview for our presentation for our projects. First will be introduction, second will be experimental setup, third will be simulation setup, and fourth will be results, and lastly will be our conclusion. So I will start the introduction part. So this project focus on determining a present operating point, which is Q point of a diode circuit. Since the Shockley diode equation produces a nonlinear equation, normal algebraic methods cannot solve it easily. Therefore, the Newton-Raphson method and second method are used to estimate the diode voltage accurately. MATLAB simulation is also used to verify the manual calculations.
My name is Qin Jingsun. I will continue to present the experimental setup and also explain about our manual calculation. From the question, we can get a general equation as shown below, and after we substitute our parameter, we will get a final equation for doing the iteration method. The tolerance we choose is less than 0.00001, which is smaller than 10 power of negative 5. We choose this value is because in physical electronic, any precision smaller than microvolt is completely discussed. For the manual calculation part, the first method we choose is second method. For this method, we need two initial guesses, which is the VD0 we choose is 0.4 and VD1 we choose the value is 0.42. After using the intermediate value theorem, we can find that there is a root between the intervals, and so we use the data to do the second method, and finally the process stop at the fourth iteration, and we can get a conclusion the root is approximate to VD4, which is 0.4145. The second method we choose is Newton-Raphson method. The initial guess for the VD0 is same with the second method, which is 0.4. We use this data to undergo the Newton-Raphson method. We can find that the process stop at the third iteration, which means that the root of the equation is approximate to VD3, which is 0.4145.
Hi, my name is Wen Jiaquan. Now, I will demonstrate how we validate these roots computationally using MATLAB. Before we start, I distribute this into four parts. First, define the problem equations. Second, the Newton-Raphson method. Third, the second method. And the fourth, verification using MATLAB's built-in function. Here in our script, we first define our nonlinear function using an anonymous function handler f. For Newton-Raphson method, we also program the exact first derivative df. We set our computational tolerance to 10 power of negative 5 to minus our manual constraints, and also a maximum number of 10 iterations to prevent infinite loops. Looking the Newton-Raphson method, our first initial guess is 0.4. And the second method, our first initial guess is 0.4 and our second initial guess is 0.42. So now I will run the script. If you look down here the command window, you can see the Newton-Raphson loops run first. Starting from our 0.4 guess, it rapidly converts to 0.4145 watt in exactly 4 iterations. And next, the second method. The second method pulls from two initial guesses. Even without the derivative, it successfully navigates the curve to arrive at the exact same operating voltage of 0.4145 watts in 4 iterations or so. Finally, to ensure the absolute accuracy, we pass our function through MATLAB's built-in F0 algorithm. As you can see, it perfectly corroborates our manual and simulate findings. So, as the result, the manual calculation stops at 4th iteration, and the root of the function is approximate to V default 0.4145 watt, and the simulation result is also converged at 0.4145 watt in 4 iterations. For the Newton-Raphson method, the manual calculation stops at 3rd iteration, and the root of the function is approximate to VD3, 0.4145 watt, and for the simulation result, the Newton-Raphson converges at 0.4145 watt iteration.
As a conclusion, we have successfully solved a real-life engineering problem using two different numerical methods by doing this project. So the engineering problem that we solve is finding the Q points of a diode circuit, and the numerical methods that we use are the second method and the Newton-Raphson method. And to verify our answer from the manual calculation, we use the MATLAB software. And from the software, we can get similar results from both the manually calculation and the simulation. And that is all from me. We are from Group 1, and thank you for your time and attention.